Hello, welcome to this session, and you're going to be learning how to build an autonomous vehicle. So, there are several layers to building an autonomous vehicle. You have the perception layer, where you take in inputs of the environment. This could be from a camera, and you want to know the position of obstacles and avoid them. You down the perception layer, you have the planning layer, where you're given a goal, position, location, and given your current location, you want to plan is an optimal trajectory that connects your current position to the goal position. And down the planning layer, you have the control layer, where you want to instruct the drones to be in a particular orientation or attitude, position, XYZ position, and velocity. So you're going to have to implement a control layer. So a drone has inertia because it's a physical object. And so what that means is if you send a command, say to move to a height 5 meters, because the drone has some mass and it's moving, it's most likely going to overshoot that desired position. So you want to prevent that overshoot or control it. And that's what the control layer does. It dampens the movement of the drone to ensure that it doesn't overshoot that desired position. And down the control layer, you need some way to estimate the state of the drone from measurements. But most of the sensors we'll be using will be noisy, and you need some way to filter out the noise from the sensors. And that's what the estimation layer is for. You want to be able to tell the velocity, the position, and the orientation of the drone accurately, well enough to command the control layer. So for this session, we'll be looking at the planning layer, because it's fun and you want your drone to be able to go somewhere and without bumping into obstacles. So there are two major representations that we'll look at. You have the graph and the grid-based representation. The grid-based representation is easy to imagine. So imagine you have a space. So we first create a space where we want our drone to fly with obstacles. This could be buildings, this could be structures, this could be trees, and your task is to design to write an algorithm that's going to find an optimal path that connects the start to the goal position. With a grid based representation, you can imagine an imaginary um, grid overlaying your search space, and the drone has a set of actions it can take to move from any state to the next state. An example of this action would be up, down, right, and left. And you could include diagonal motions if you want a more robust planner. And with these actions that allow state transition, the next step would be to test if a given state is feasible. So we can have a simple definition that is, if a state falls into an obstacle or whatever we tag as an obstacle region, then that state is infeasible and we discard that state. So with this, we have a definition for selecting a state, and with the actions we discussed previously, we have a set of rules for state transition. Next would be a way to navigate our grid-based representation, and for this, we'll be using an A-star grid search algorithm. Now, the A-star grid search algorithm is the A-star algorithm modified to search through a grid. And so we start up with the current position of the drone, and we check all possible actions we can take, and we check the states that that leads into, and then we check if that's a feasible state. And if it's a feasible state, then we add that to our list of partial plans. And eventually, you're going to have some heuristic for selecting a more optimal partial plan. And for this scenario, we'll be using the distance from a current state to the next state, and which is the distance that the straight line distance that connects the point. So the A-star algorithm is robust enough for you to define your heuristic, but um, for working with the physical world, where we're planning and we're flying or navigating through the physical world, we're going to use distance as a heuristic. So with this heuristic, we'll have a way for selecting shorter state transitions that involve shorter paths, and eventually would choose the shortest path that connects a start location to the goal location. The problem with this approach is that for my little drone here, with the Arduino microprocessor, you have just kilobytes of RAM, so you don't have so much RAM. And if you have a 3D grid based planner, which involves voxels, which are blocks that are spread around your space, and then you have to search through these blocks, you're going to quickly run out of memory. You're going to need megabytes of memory to store all the spatial plans. So you're going to outcompute your Arduino Mega. So we need something more efficient, a representation that's more efficient than the grid-based representation, and that brings us to the graph-based representation. So a grid is an example of a graph, and for a graph, you're looking at a set of edges that connects points, and because they're all interconnected, we have a graph. So we're going to look at the probabilistic roadmap algorithm and planner, and the first thing to do would be to set out to spread out random points. So we can choose 40 random points that saturate our search space. So 40 points within the search space, and then the next step would be to check if any of these points is infeasible. And by that I mean, if by our definition of infeasible would be if this point collides with an obstacle, then we disregard that point. So we eliminate points that lie within an obstacle, and we're left with points that lie around the obstacles, right? And the next step would be to try to draw an edge from any given point to the neighboring point. And we want to ensure that the edge that connects a point to the next point that represents a state transition does not cut across an obstacle. So if it does cut across, then we eliminate that edge and we disregard a connection between that point and that other point. So when we do this, we end up with a graph with edges that avoid the obstacles and represent the connections and interconnection of the selected points. So the advantage of the graph-based representation is that you have, because we have 40 points, depends on our specifications, we have a much more finite number of points, and this leads to a less computationally intensive um, search process when you implement your A-star graph search algorithm. And for the A-star graph search algorithm, very similar to the A-star grid search, we modify the representation to be a graph, and we specify that the cost between any state, which is a vertex, to the next would be the edge, the length of the edge that connects that current state to the desired next state. And we find the A-star search graph search algorithm would return the path that connects the vertices, the shortest path that connects the vertices. Now this is the A-star graph search probabilistic roadmap planner. Now, because you have a set of waypoints, you'd expect that the drone from one waypoint reaching the other waypoint would stop. So you have a non-smooth trajectory. So I challenge you to prove that as long as you have a physical object with mass and moving along a waypoint, that the and given the condition that the drone does not stop at any waypoint, you're going to have a continuous motion where you're going to overshoot the waypoint because of the mass, but then you're going to have a continuous and everywhere differentiable motion. That's your task, and that's what you're going to prove when you're done with your planner. That's just a bonus. So it's a really exciting course because eventually you're going to be able to try this out on your drone, just like I'm about to do. So enjoy the course, and if you have any challenges, I'll be right there to help you. Bye.